Dipole-dipole interaction. Dipole-dipole. Have you ever heard of tug of war before?
Yeah.
Can you tell us something about tug of war?
It's an interesting game. So there is a rope, a strong rope. Sometimes they draw a line in the middle part of the rope. Then there are two people at each end. One person at each end or a group at each end. So they'll be pulling each other. The group or the person is able to pull the other person to the side or to cross the line to get to the other person's side. That person has won.
So that means the stronger group pulls the weaker one.
Yeah.
Okay, so that's tug of war. Interesting. And funny enough, atoms also sometimes engage in tug of war. The stronger one pulls the weaker one, especially when they are involved in covalent kind of bonding. So the stronger one pulls the weaker one. I will get to understand that in dipole-dipole interaction. But for us to understand what dipole-dipole interaction is, the first thing we have to understand is what a dipole is. So what is a dipole?
A dipole is a polarized molecule having partially positive and negative poles.
Good. So the point we want to stress on is positive and negative poles. Partially positive and negative poles. We'll explain what a dipole is using chloromethane. Chloromethane. That is what you have on the screen. CH3Cl. Chloromethane. So chloromethane is formed from a bond between carbon, 3 hydrogens, and a chlorine. That's how chloromethane is formed. So to form chloromethane, the hydrogens, the 3 of them and chlorine, overlap with the carbon to share pairs of electrons. So there are 3 carbon hydrogen bonds and then 1 carbon chlorine bond. Now this is what happens. If you look at the carbon hydrogen bond, the one at the top, this one, there are 2 electrons. That is 1 pair of electrons that is being shared between the carbon and the hydrogen. This electron that is being shared, surprisingly or interestingly, because carbon is stronger than hydrogen. In the terms of chemistry, we don't use stronger, we use more electronegative, meaning it loves the electron. It loves electrons. It loves to draw electrons towards itself. Because carbon is stronger or more electronegative than hydrogen, it pulls the shared pair of electrons towards itself. I hope that's clear.
Yeah.
Then it doesn't end there. There is another carbon-hydrogen bond. That is the carbon by the side, the hydrogen by the side. There is also a shared pair of electrons. This shared pair of electrons is pulled towards carbon. Then this third hydrogen, there's a shared pair of electrons between the hydrogen and carbon. This shared pair of electrons is also pulled more towards carbon. So what does that mean? In simple terms, the electron cloud around these 3 hydrogens are dragged or pulled more towards carbon. So what becomes the result of this pull? The 3 hydrogens end up becoming partially positive. And if the 3 hydrogens become partially positive, what it means is that the carbon becomes partially what?
Negative.
Good. The carbon becomes partially negative. And negative because it pulls electrons towards itself. And electrons are negative, right?
Yeah.
So if it pulls electron more towards itself, it will end up being partially what?
Negative.
Partially negative. But it doesn't end there. You see, there is a carbon-chlorine bond. Between the carbon and the chlorine, they are sharing this pair of electrons. Now, the question is, carbon and chlorine, which is more electronegative? Obviously, it is what?
Chlorine.
It is chlorine. Chlorine is more electronegative than what? Carbon. So that means that chlorine is going to pull this shared pair of electrons more towards itself than carbon will. Carbon is trying to drag. chlorine will also try to drag. So carbon is trying to pull the shared pair of electrons towards itself. But who wins? Chlorine. So you see chlorine is pulling with much higher force. That is indicated by the bigger arrow. So chlorine will pull the shared pair of electrons around, or the electron cloud around carbon, more towards itself. So as a result, although chlorine or carbon tends to be partially negative when we're looking at the carbon hydrogen bond, because chlorine is much more electronegative, it pulls it. So carbon now tends to be what? Partially positive. It also now tends to become what? Partially positive. And the chlorine becomes partially what? Negative. So this is what happens. The hydrogens and the carbon, all these four atoms, are then pulled towards chlorine. Their electron cloud, the electron cloud around these four atoms are all pulled towards chlorine. Why? Because chlorine is more electronegative than what? The four atoms we have out there. So look at what happens. That means this chloromethane can be divided into two. Based on their charges. Look at this. All the ones to our left are partially what?
Positive.
Are partially positive. Because you can see the three hydrogens. Then the carbon tends to be partially positive. So in terms of charge, all of them are partially positive. And then the chlorine is what?
Partially negative.
Partially negative. Good. So we have how many poles? 2 poles. A positive pole and what? A negative pole. So that will be 1 positive and what? 1 negative pole. But in chemistry, instead of we saying 2 poles, we say what? Dipole. So that's how come the name came about. So dipole simply means 2 poles. And the poles we are talking about are what?
Partially positive and negative poles.
Good. Partially positive and partially negative poles. Now, this type of dipole is known as what?
Permanent dipole.
Good. So this is a permanent dipole because chloromethane will always have a part that is partially positive and another side that is partially negative. That's why it is considered a permanent dipole. In our next lesson, we'll be considering what a temporal dipole is when we get to induced dipole interaction or London dispersion force. Now that we understand what a dipole is and what a permanent dipole is, I think we can now move on to explain what a dipole-dipole interaction is. So what is a dipole-dipole interaction? So now we have chloromethane, which is a dipole molecule, a molecule that is dipole. So what is a dipole-dipole interaction?
So dipole-dipole interaction is an intermolecular force of attraction between polar molecules, meaning molecules that have a permanent dipole.
Good. So our focus is on molecules with what?
A permanent
dipole. So it is an intermolecular force of attraction between what? Polar molecules. Now, in order to explain what a dipole-dipole interaction is, using this diagram of chloromethane, let's consider this molecule of chloromethane. This is one molecule of chloromethane. Let's assume there is another molecule of chloromethane. If you pick this one molecule of chloromethane, the chlorine is partially negative and the hydrogens are partially positive. The partially negative side of one of the molecule becomes attracted to the partially positive of another molecule. Then let's assume there's another molecule of chloromethane. It also has a partially positive hydrogen and partially negative chlorine of the next molecule. They also get attracted. Let's assume there's a fourth molecule of chloromethane. The same thing happens. Partially positive of the hydrogen of one of the molecules is attracted to the partially negative chlorine on the other molecule. So each of the molecules, chloromethane, is a dipole. So the interaction between the two dipoles, two or more dipoles, is what is known as what? A dipole dipole interaction. I think that makes sense.
Yeah, it does.
Good. And take note of this. We are representing the dipole-dipole interaction, which is an intermolecular force of attraction with dotted lines. They are shown with the red dots. So remember the definition of a dipole-dipole interaction. It is an intermolecular force of attraction between polar molecules. So the polar molecules you have on the screen for us is chloromethane. So the dotted line represents what? A dipole-dipole interaction. Now, dipole-dipole interactions, are they chemical bonds?
They are not chemical bonds.
Good. They are not chemical bonds. And the reason is simple. Because they are not found between atoms. In our previous lesson, when we were discussing covalent bonds, we spoke about covalent bonds, which are specifically in terms of organic compounds that we have been discussing so far. They are intramolecular forces. They are the chemical bonds that hold the atoms together. If you want more explanations on that, you can check the description of this video to find a link to that video. Or you can check our playlist and you have access to that video as well. So dipole-dipole interaction is an intermolecular force of attraction, not intramolecular, which happens to be a chemical bond. And one interesting thing about dipole-dipole interactions is that they are basically weak. They are weaker than covalent bonds that we've studied earlier. Now, there are some other compounds, basically inorganic compounds, that also have dipole-dipole interactions between their molecules. We have HCl, they have hydrogen fluoride, and also have water. So water also exhibits this kind of dipole-dipole interaction. But for water molecule, there's a special kind of dipole-dipole interaction that exists between water molecules that we'll be discussing in our future video. That is more specifically hydrogen bonding. We'll be considering that into detail in future video. So now what are some properties of dipole-dipole interactions?
So one of them is that they occur between polar molecules.
Good. And remember we spoke about what polar molecules are, especially the dipoles. And they happen between permanent dipoles. And we already explained them to be having slightly positive and negative ends. And examples of molecules that have them are HCl and chloromethane that we already discussed, and SO2. What other property do we have?
They are also stronger than London dispersion forces.
Good. So in our next lesson, just after this, we'll be explaining what London dispersion forces are. And you get to know why they are weaker than dipole-dipole interactions. So dipole-dipole interactions are stronger than London dispersion forces. But interestingly, dipole-dipole interactions are weaker than hydrogen bonds. A hydrogen bond is a special type of dipole-dipole interactions anyway. So when we get to hydrogen bond, you'll get to understand the explanation of it. And why we said in an earlier slide that it is the chief intermolecular force of attraction between molecules of water. So this brings us to the end of this lesson. In our next lesson, what will we be studying?
So we'll be considering the London dispersion forces into details.
We'll London dispersion forces into details. So if you follow the video all the way to this point, all that means is that maybe you find the lesson helpful. So subscribe to the channel so that we didn't miss our next lesson. But what are we to expect in the next lesson? London dispersion force. This is a trailer. We'll explain what a temporal dipole is. We have some interactive images to see how the movement of electrons in atoms lead to the formation of temporal dipoles. And then we'll link that to induced dipole and explain what London dispersion forces are. So see you in our next lesson.